Good evening. Welcome to the May presentation of the Naperville Astronomical Association. I'm Drew Carhart, president of the club, and we're giving this a try again to see how well we can do in the virtual space of the internet. We have a few announcements that I do want to go over before we start tonight's presentation. Wanted to thank you all for joining us. And as I pointed out last month, I wanted to remind people that if you're viewing on Facebook or in the embed on our club website page, you can maximize your screen view instead of looking at a little box. Down in the corner, in the right-hand corner generally of your screen, if you see a little toolbar, you may have to put your finger or your mouse over that to see it. There'll be a little maximize button, which is a square with made of 4 arrows. If you hit that, it should fill your whole screen up so you can see the presentation more clearly. If you have any questions during tonight's program, we can take questions from the viewers in 2 different ways. If you're on Facebook, you can just use the comments section and put your questions in there. Our engineer, Jim, is watching the Facebook feed, and he's going to try to catch any that are directed at the speaker, and he will pass them along to the speaker at various times during the presentation. If you're looking at our website, or it's easier for you just to use email, you can send us an email at this address at feedback@naperastro.org. Jim's also watching that account for questions that may come in, and in fairly real time, we will try to pass those along to our speaker also. And as I noted last times we've done this, we'd also always welcome suggestions for what we can do with our programming in the future. I wanted to run quickly through some upcoming events. On the 19th of this month, we have our Astronomy Fundamentals program, of course, being presented online like this in the same venues. This month it's going to be on asterisms, or the patterns in the stars. And if you want to learn more about constellations and their smaller cousins, the other asterisms in the stars, that's what this presentation will be about. On Tuesday, the 2nd of June, our June presentation probably is also going to be online like this. It's unlikely that we'll be having live meetings that soon, but the presentation in either case will be on the Apollo Moon program. And the best advice is to be following our calendar on our website, and we'll keep you up to the minute, up to date, if we do go back to having live meetings. We might, even if we do that, we might still stream. That'll be something we'll have to work out. But follow the calendar on the website, and also we'll post obviously on Facebook too when we have updates about the the nature of the June presentation. And then we do some pop-up events. We're even talking about maybe doing one later this week, which would generally be things at our observatory. So watch us on Facebook, and that's where we'll note it. If you're a member of the club, we'll put it on the club message board too. This evening, we have a guest speaker in. Dr. Eric Coles is our presenter, and he is going to, did I go backwards there? That's not what I meant to do. He is going to tell us about not his job, but his hobby. Dr. Coles is a research biochemist with extensive experience in biotech startups and drug development. He's had research appointments at Columbia Medical School and at Harvard Medical School. But as a hobby, Eric has collected more than 600 images that he has taken and processed over the past 9 years. His astrophotography is recognized worldwide for its representation of these deep space objects and for all their detail and artistry as well. To date, 10 of his images have been selected for the Astronomy Picture of the Day website, which I'm sure many of you are familiar with. So without further ado, I would like to introduce Dr. Coles, who is going to speak to us about the Hubble Palette and give us a demonstration about how you create wonderful images out of digital information. So let's see if we can get transferred over to Dr. Coles. And I think we're ready to go.
Thanks very much, Drew. Am I on the main screen now, Jim? I have to share my screen?
Yeah, we're ready for you to share your screen.
Okay, share screen. All right, thanks again, Drew, and thanks to the Naperville Astronomical Association. Tonight, I'm going to talk about some of the pretty pictures that we do in astrophotography. That's exclusively why I do this. I don't want to say there's no science involved, but basically, I do it just to have these pretty pictures eventually appear on my screen. And that's kind of my joy in life. So let's start out with a short video, about 3 or 4 minutes long. And after that, we'll start some processing. Okay. Well, I'm sure you're paying attention. If you saw the image of the Great Pumpkin Nebula, that's not really something you see in the sky. That's just something I concocted with Photoshop. We do this for fun. It's not just about pretty pictures, or if it is, it's about pretty pictures that make us smile. And the Great Pumpkin Nebula was a combination of an image I just generated from an astrophotography and a pumpkin. Okay, let's get started. We're going to do what's known as a Hubble Palette image, which is a mapped color image. We see things in an RGB, that is a red, green, blue palette. But most of the images you see from, say, the Hubble Space Telescope are mapped color images. That is, the colors that you see on the screen are not the actual colors that they see in the sky. And here down on Earth for our astrophotography, we use filters that separate out the emissions of three different elements: hydrogen in the hydrogen alpha emission, sulfur in the sulfur 2 emission, and oxygen in the oxygen 3. And those are the approximate colors that we see through those filters. But when we apply them to an image, we don't apply them as those colors. We apply them as RGB colors. And the way we do this is we say the sulfur, which is really a deep red, is going to be our red color in the RGB palette. Hydrogen alpha, which is also red, we're going to make that green. And oxygen 3, we're going to make that blue. And that's our RGB. That's called mapping colors, not natural colors. And almost all the images you saw in that short video are mapped colors. So let me open up the first program that we're going to work with, and that's called Pics Inside. Now, you don't have to be an expert in Pics Inside to understand what's going on here. So before we start any processing of an image, we collect a lot of data. And I collect data primarily from a telescope that's out in California at a very dark site called the Sierra Remote Observatories. And for this particular image, which is the Rosette Nebula, an emission nebula, that is an emission nebula, I'm sure you all know, is a cloud of gas, usually in the vicinity of a bright star, and the bright star excites the electrons in those three elements, those spectrum you saw just a few minutes ago. And as the electrons are promoted to a higher energy level, they eventually fall down and emit light. That's why it's called an emission nebula. So I collected data on those three filters, maybe 3 or 4 hours for each filter. And I'm going to bring up those three filters right now. Let's open up a stacked set of data from the sulfur, oxygen, and hydrogen alpha collections. Open, and here are the files. Let's move them over here. Okay, well, what do we see here? We don't see anything. We don't see any structures. We see the little kind of red, white dots here. These are all grayscale images, but we don't see anything that looks like an emission nebula. And why is that? Well, that's because most of the information is parked way, way down on the lower end of the scale. Let me bring up the histogram of hydrogen alpha. Now, a histogram is just a representation of the different levels of gray that you see in these collected images. And these are 8-bit images, and so we have 256 shades of gray from basically black over here on the left all the way to complete white at 256. So we don't see anything in these images because all the information is really clustered right down here next to black. So what we have to do with these images, we have to stretch them. That is, we have to take this point here and stretch it and fill up some of these gray areas between black and complete white. So I'm just going to do what's known as the default stretch. I'll click on hydrogen alpha, and I'll hit the little stretch button. Oh, there we go. We have an image. That kind of looks like a rosette. Now, I haven't actually changed this particular image. This is still what we would call a linear image. It's still as we collected it and stacked from the original data from the telescope. But this is a representation of what it looked like if it was going to be stretched. And so now I'm going to implement this stretch so I end up with a nonlinear image. And the way I do that is just drag this caret over here. Of course, we're going to turn off the auto stretch now. And now we have a nonlinear image, and we see we have shades of gray all the way from black up to about the 60% of white. And we see an image that we can actually recognize as a structure. So this is a hydrogen alpha image of the rosette and about 3 to 4 hours of collected data. And I'm going to do the same thing for the oxygen. We're going to implement default stretch. And turn off the auto stretch. And the same thing for the sulfur. So now we have 3 nonlinear images which are showing the structure of the Rosette Nebula using the hydrogen alpha filter, the oxygen 3 filter, and the sulfur 2 filter. And the interesting part of this is that the distribution of hydrogen and sulfur and oxygen is obviously different. So ultimately, when we apply these and call one of them red, one of them green, one of them blue, that we're going to get a color image which is going to represent the distribution of those 3 elements in this emission nebula. So I've already done this, so I have saved these 3 as nonlinear images in another file, which I'll open up a little bit later. So I'm going to put this aside. Now, in order to do what's known as the Hubble Palette and tone mapping, which I'll explain a little bit later, we have to generate an image which does not have any stars in it. So I have to take out all those stars. Now, you don't have to know exactly how this is done, but I'll just give you a short demonstration. There's a utility here in Pics Inside, which will take out the stars, and it's called StarNet. But if I cause that to happen, then it'll take about 2 or 3 minutes and we'll have dead air and we won't be able to do anything. So we're not going to do it in real time. So what I'm going to do is I'm going to, let's see. We're going to do a dynamic crop, and I'll show you just a little bit about how the stars are taken out. I'm going to make a copy of the rosette, and I'm going to just crop it right down here. So there's just a little bit of the rosette and a few stars. And this will take about 15 to 20 seconds, and when we're done, all the stars will be gone out of this particular image. And I'll explain why we're doing that in a little bit once we get over the Photoshop. So I don't have any music to play while this is happening, but it should only take about 15 seconds. And we're going to generate starless image out of the 3, the sulfur, the hydrogen, and the oxygen images that you see right behind this one. Oh, there we have. All the stars are gone. We don't have to know how this is done, but it's a nice utility. And we're going to take the stars out of these 3 images. So let us say, I'll put this over here, that we have generated the starless images. So we have the 3 nonlinear images showing the distribution of sulfur, hydrogen, and oxygen. And I'm going to close those down, and you can assume that I've saved them, and I'll open them up in another folder. And now, just for grins, let's open up the starless images. So there's our 3 starless images. The hydrogen alpha, the sulfur 2, and the oxygen 3. And again, we see that there's a different distribution of these 3 elements, which we're going to represent in Photoshop as RGB. We're going to map them to red, green, and blue so we can see them in a nice color palette. So I think we're done with these images.
Hey, Eric, we have a question from Facebook.
Sure.
So Jim is asking, does the Hubble telescope use these same 3 element filters for its pictures?
No, it doesn't. No, in fact, Hubble Palette or Hubble telescope does not have red, green, and blue filters. I'm going to open up something else here. Let me put this over. Yeah, I'll put it over here. No, the Hubble telescope has all sorts of other filters, some in the visible and some in the infrared and some in near infrared and some in the ultraviolet. And when they take images of certain structures in space and they want to represent, say, infrared data, they have to do it in RGB. So all of the images you see from the Hubble Space Telescope are all mapped images. They have a whole variety of filters, and they have to map them to the red, green, and blue palette in order to come up with the images that you see. They do not represent how these things actually look. In fact, if you take RGB images, which are somewhat natural, say from a ground-based telescope, and compare it to what's done with Hubble, they look different. They are not the same. So the question is, what color would these emission nebulas be if we just took natural color images? We just use red, green, and blue filters. Let's not do that. Let's do it this way. I like that nice black background rather than the white background. So what color would the emission nebula be if we just use RG and B filters, which are 100 nanometers wide rather than 3 or 4? I would say someone should answer that, but the answer is this. They're all red. Every one of them, some maybe are a little bit orange or a little bit blue, depending on whether they have more oxygen emission. These are all emission nebula taken with RG and B filters, not with narrowband filters. All right, I think we're done with that. So red is a nice color, but I think that you've seen lots of the Hubble Palette image even without knowing about it. And you can say that they're much more interesting. So now we're going over into Photoshop. Some of you may have experience with Photoshop, but even if you don't, I think you'll be able to understand what we're doing next. So let's open up our starless image. These are the 3 images that we generate. I kind of generated them offline since it would take 10 or 15 minutes to do it live, and that's probably not very exciting to watch. So let's say we took the nonlinear image, we took the stars out, we saved the starless image, and now we're going to open them up in Photoshop. Here we have the sulfur, oxygen, and hydrogen alpha. So we're going to map them as follows, just to repeat. The hydrogen alpha, which is the strongest emission in almost all emission nebulas, except for maybe 1 or 2 I can think of, is going to be mapped to green, even though it is really red. The oxygen, which is kind of blue-green, we're going to map to blue. And the sulfur, we're going to map to red, even though it's a very deep red. So how do we do that? So I'm going to take a copy of the hydrogen alpha image. I'm going to copy the whole thing. I'm going to make a new image, and we want to make this as RGB, and we're going to paste it in. And I'm going to bring up the channels. So if you're not familiar with channels, this is a red, green, and blue image, and we have a red, green, and blue channel. And right now, the hydrogen alpha is mapped to all three of those channels. So let's go back and grab the oxygen starless image. Copy. Go over to our new image, and we're going to put it in the blue channel. That is, we're going to map it to the blue channel. And we're going to go back and take the sulfur, copy it, and we're going to map it to the red channel. And there we have the beginning of a Hubble Palette image. Now, let's see, do I need these others? Yeah, let's keep those open for a while. Let's just save our work here. Let's call this Hubble Palette 3. Now that's still really dominated by the green color. And the reason is that even after I've stretched out those three starless images, there's a lot more hydrogen alpha than there is oxygen and sulfur. And if you look at Emission Nebula, as we just saw on those pictures that I flashed through, what color are they? They're red, and that's primarily because of the emission of the hydrogen alpha. Let's go back to the layers. So we're going to make some adjustments in this to kind of balance out the red, green, and blue to get closer to the kind of image that you probably see in Hubble Palette images. And I'm going to open up, I'm going to make a copy of this layer. I'm going to open up the histogram. You remember our histogram, and here you see the green and kind of the red and the blue underneath it, and the green is really predominant. So I'm going to go in Photoshop, and again, you don't have to know how this works, but there is an adjustment called the levels, and I'm going to adjust the histograms to try to balance out the red, green, and blue as best I can. So let's go and change red. Well, that's looking a little bit better. Now, a Hubble Palette image really goes from kind of a deep purple to kind of a dark orange. And we're getting pretty close to this. Now, remember, we don't have any stars yet, so we're going to put in those stars a little bit later. But I want to make one more adjustment here. I'm going to make another copy of the layers. And there's an adjustment that was developed by a fellow by the name of Bob Franke. And if anyone's interested in doing this, I can give you the reference. But instead of going through step by step, the Bob Franke adjustment, so let's label this is the levels adjustment. And this is the Franke adjustment. And I have turned his adjustment into, let's see, I got it here in a little action in Photoshop called the tone map adjustment. I'm going to play this adjustment, and wow, that's starting to look like a real Hubble Palette image. So this is what's known as a tone map. Each of those starless images is a tone map of that particular element. That is a tone map, that is the mapping the intensity of that particular emission over what is there, an 8-bit scale, 0 to 256 shades of gray. So we have a tone map of the 3 narrowband filters, and I've combined them to produce a color tone map of a Hubble Palette. So this is a Hubble Palette tone map, but we still don't have no stars. So let's try to put our stars back in here.
Eric, we have a Facebook question.
Sure, go ahead.
This might derail you a little bit, but the question was, what kind of results have you got with hydrogen alpha, oxygen, and sulfur from like the Chicagoland area? Are there any reasonable targets that a beginner could start with that doesn't have access to a telescope, under great dark skies?
The answer is yes. In fact, that's about the only kind of imaging you can do from Chicagoland, and the kind I did for probably 2.5 years when I got started was right from my back deck in Glen Ellen. And the reason you can do this is that these narrowband filters are, the ones I have are only 3 nanometers wide. And therefore, all this light pollution that we have around here, all these terrible skies, most of it is filtered out. You can do lots of very nice narrowband filtering, especially hydrogen alpha, in a whole set of targets, primarily in the late summer and fall. You just have to point your telescope, have a good view to the north, and you can take an image of the Rosette Nebula. In fact, my first images of the Rosette were taken right here in Glen Ellen. So the answer is yes, you can do narrowband photography right here. Now, if you want to do RGB photography with filters that are 100 nanometers wide, you better go someplace else, because that's very difficult to do with our light polluted skies. So the short answer is yes, you can. So let's put this.
We have one other question. Sorry.
Oh, sure.
Jim was asking, I think, about the Rosette Nebula. He said, is this an emission nebula? So it emits these specific elements. Would you ever do a monochrome image channel to add to these? Isn't that called a luminescence channel?
Why don't we hold that question and I'll answer it in just a moment.
Sure, thank you.
Okay, so yes, what we're missing here is adding the stars back in, and we're going to do that with the hydrogen alpha that's functioning as a luminescence image. Great question, just in time. So let's open up our nonlinear hydrogen alpha. There it is, you remember that guy. And let's use that as a luminescence layer. I'm going to make a copy of it. We're going to put it right on top of our tone map. Now, what is a luminosity layer? Okay, luminosity layer is it's like a bunch of film, and the lighter the area is, the more it shows through the information down below. That's a luminosity layer. So it allows information from the lower layer to shine through to the top layer. And if I set the merge of this layer to luminosity, the last selection in Photoshop, watch what happens. Wow. And now we have stars, because the hydrogen, let me just do that again. Let's just make a copy of that. And let's set this to normal. So if we zoom in on that, see, the stars are white, so everything down below is going to shine through. It's going to shine through as white. Ah, look at that, it's white. So the hydrogen alpha is our beginning, but not the end, luminosity layer. Now I'm going to adjust the levels on this a little bit to darken it up because it kind of fits my eye. And as you're doing astrophotography, there is no endpoint. There's no place to get to. There's no finish line. The only thing that you should go for is something that pleases your eye. This is really art, not science, even though it is representing some scientific information, which for most of us in this field is interesting because most of us are technical people. So I'm just going to adjust the histogram and darken this up a little bit. Let's just move the histogram along here, make it a little darker there. And why am I doing this? Because it appeals to my eye, not because it's right or wrong. And you see we have the typical Hubble Palette image with white stars. The reason we have white stars is that star color has no meaning in a Hubble Palette image. You have to think about that. We do have images that are RGB, and their star color does make a difference, but not here. Now, what's missing out of this? Well, a couple things are missing. So we have our luminosity as a hydrogen alpha, but what about the contribution of the sulfur and the oxygen? We don't have that here. So we're going to add some of that contribution. And the way we're doing this is by taking the starless image from sulfur. I'm going to make a copy of that. I'm going to put it on top here. And I'm going to combine it by means of a screen. That's too bright. And now I need about 20% of that. And I'm going to merge that down. Now we have a contribution in luminosity from the sulfur. And I'm going to do the same thing for the oxygen. Copy. Paste it on top. Screen at 20%. Let's do a little more. Let's do 25%. And merge it down. And now we have contribution to the luminosity, which means what shines through from the tone map of all three elements. And now I'm going to make a little adjustment to the levels because I think this is just a little too bright.
So I think we have a question about these levels. Donna is asking, why are you basically, I think what she's saying is, why are you only moving that on the left side? So her specific question is, why do you need to perform the stretch? What is it about the camera response that makes the pixel values clustered in just one end, the very dark in your example?
Because there isn't much light coming down in these narrowband filters, that's why. They are very, very dim. And even after you collect 3, 4, 5, even 10 hours worth of information on, say, a 3 nanometer hydrogen alpha filter, there isn't that much information. And we saw the way those stacked images look. All the information is very much down towards almost black and only the stars shine through. But there is information there, and that's why we do a stretch. That's what the stretch is all about. I might also say that once you do the stretch and go to a nonlinear image, that all the scientific information goes out the window, that no real astronomer does anything like this. These are just people like me that like to take pretty pictures. I don't know if that answers the question. By the way, if you do RGB images and you look at the histogram of stacked images, there's a lot more information that you can see without stretching, and you have to do actually less stretching. But for narrowband images that are so narrow, there just is not a lot of light that comes through. In fact, you kind of know that. If you look through a telescope and you looked at Emission Nebula, what do you see? You don't see any of these colors. In fact, I don't think there's maybe 1 or 2 emission nebulas that you can see anything in your naked eye. So unless you have an eye as big as a giant squid, you're going to see basically black with some stars. The same thing that we see when we look at the linear images in Pics Inside. We see a black image with a few stars. It's only the stretching that brings out this structure. All right, so I'm going to get a little more detail into this. And this is a trick in Photoshop where I take the starless image, the tone map for the hydrogen alpha, make a copy of that, and I'm going to put it on top of our rosette. And I'm going to make a couple of copies of this. And put all those copies in a folder. And I'm going to perform what's known as a high-pass filter. So let's just do it, and I'll try to explain what's going on. There's a lot more detail here, and we'd like to bring that detail out. Let me move here. This is an area which I'd like to get some more detail. So I'm going to do what's known as a high-pass filter here. We're going to take and clip the information in this histogram, so we're only looking at something 1 pixel wide right in the center. So let's just look at the histogram. So this is a nice wide histogram for this starless image. But I'm going to clip it so that I only get something 1 pixel wide, and I show the edges of all these nice structures. So there's a filter, other, high pass. And we're going to go with something, let's go with something 2 pixels wide. Now, what do you see? You see a gray image with some outlines here. So I've effectively outlined some of these dark structures in the nebula. And I'm going to click OK. And now when we look at the histogram, oh, look, it's very, very narrow, but it has outlined things that I'm interested in highlighting. So I'm going to overlay that on top of the image below. And what just happened there? I don't know if you can see it on the screen, but I got a little more detail here. Things are standing out better than they were before. So I'm going to do another high pass filter. Make my cut 4 pixels wide. And overlay that. Now you can definitely see that there's more detail. It's like bringing things into focus. And let's back up. And let's just do one more. I'm going to bring out some larger structures by going in, doing a high pass filter, and now let's go out, let's say 12 pixels wide. And now you can see we're bringing in some much larger structures. We're going to highlight those by making this an overlay. And now we've got a lot more detail that's showing out. Can you see that on the screen? It's pretty obvious here, but might not be as obvious on the broadcast. But when I implement the high pass filters, call this high pass, we're bringing out a lot more of the structure and the detail of a nebula. And I think we're done with this particular image. So I'm going to save it. Now, I've kind of lifted the curtain on what's going on. And you may say, well, gee, you know, that's not really how the thing looks in space. The answer to that question is we can't really see it in space. And we can only see these different structures by doing things like mapping and bringing out details. I say in most of these talks that there's 3 things that you don't want to see being made. And that's sausages, laws, and astrophotography images. So you've just seen the 3rd thing you don't want to see. But you do produce some nice, pretty pictures. This is kind of a breaking point. Are there some other questions that I might be able to answer here?
Yeah, we do have one from Steve. He asked if there are any solar system objects that the same Hubble Palette processing would apply to?
No, there are not. These are strictly for emission nebula. But as far as mapped image, when you do galaxies, you can do mapped images. In fact, I'm sure if you read the astronomy news, you find out that the Spitzer Space Telescope was just decommissioned. Spitzer takes pictures in infrared. They produce some beautiful pictures, but none of those wavelengths are things that we can see. So every one of the Spitzer Space Telescope images are all mapped. That is, they take different cuts of infrared and they map them to red, green, and blue to come up with some really fantastic pictures. In fact, I think I've taken a couple of the Spitzer pictures and I've registered them and combined them with some pictures that I've taken. You could actually take the Spitzer Space Telescope image and combine it with this Hubble Palette image that I've done here. Any more questions? So this is a mapped Hubble Palette image of the Rosette Nebula. By the way, this one, well, let me just bring one more thing up here. Give me just a moment. Let me search something out that I probably should have done earlier.
We do have a question that just came in.
Okay.
Jim asked if I want to improve the contrast on seeing Emission Nebula with my telescope from suburban skies, what's the best filter to use? That might not necessarily be a you question.
It might not be a you question. The answer is there just is very little that you can see in Emission Nebula. I'm trying to think of the only Emission Nebulas where you can see any color at all. And I think you can see it with the, I think you can see some color with the Ring Nebula and maybe one or two more. But I'm not really a visual astronomer. I just take pretty pictures, so, unfortunately. Or
we'll try to answer that question to him.
So here is an APOD of a couple of years ago of the same data in a Hubble Palette image. And you might notice that this is a little different as far as color tone from the one I just did. And the reason is that every time you go through it, there is no endpoint. It's something that fits your eye. But this is exactly the same data that we just processed. Now, the interesting part of this APOD is both kinds of images are represented. Now, if I roll over it, that's what an RGB rosette looks like. RGB, Hubble Palette. Which is more interesting? Probably depends on really what you like. I wouldn't say one is more interesting than the other. So let's close that down. Yeah, this is a little different. I guess it's just what appealed to me today as I went through it. Next time I do it, it might be a little bit different as well. This is art, not science. Are there any more questions? I have one more thing to kind of play for us.
No more questions at the moment.
All right, I have one more video to play.
We're all connected to each other biologically, to the earth chemically, to the rest of the universe atomically.
I think nature's imagination is so much greater than man's. He's never gonna let us relax.
We live in an in-between universe where things change alright, but according to patterns, rules, or as we call them, laws, forces of
I'm
nature.
this guy standing on a planet. Really, I'm just a speck. I'm just a speck compared with a star. The planet is just another speck. To think about all of this, to think about the vast emptiness of space, billions and billions of stars, billions and billions of specks. The beauty of a living thing is not the atoms that go into it, but the way those atoms are put together. The cosmos is also within us. We're made of spark stuff. We are away from the cosmos to know itself.
Across the sea of space, the stars are others. We have traveled this way before, and there is much to be learned.
We're all connected to each other biologically, to the earth chemically, to the rest of the universe atomically.
I find it elevating and exhilarating to discover that we live in a universe which permits the evolution of molecular machines as intricate and subtle as we.
I know that the molecules in my body are traceable to phenomena in the cosmos. That makes me want to grab people in the street and say, have you heard this?
The beauty of a living thing is not the atoms that go into it, but the way those atoms are put together. The cosmos is also within us. We're made of spark stuff. We are away from the cosmos to know itself. There's this tremendous mass of waves all over in space, which is the light bouncing around the room, going from one thing to the other, and it's all really there, really there. But you gotta stop and think about it, about the complexity, to really get the pleasure. It's all really there, really there. The inconceivable nature. To think about all of this, to think about the vast emptiness of space, billions and billions of stars, billions and billions of specks. The beauty of a living thing is not the atoms that go into it, but the way those atoms are put together. The cosmos is also within us. We're made of spark stuff. We are away from the cosmos to know itself.
Across the sea of space, the stars are others. We have traveled this way before, and there is much to be learned.
I think I'm done. Thank you.
Eric, we had a few more questions come in.
Sure.
Frank asked, is hydrogen beta a useful wavelength?
There are about 5 narrowband emissions that you can use, including hydrogen beta. It's not nearly as strong as hydrogen alpha and doesn't represent another structure. Remember, the idea of the narrowband filters is to define regions where those elements exist. So since hydrogen alpha is much stronger than hydrogen beta as far as emission, and I think the filters are easy to make too, that you really only need one of them. But you can use hydrogen beta, but it'll just show distribution of hydrogen.
And then Tony asked, how much time does the actual processing take on average?
Somebody asked that the other day. If you spend 20 hours collecting data, you're going to spend 15, 20 hours of processing. Now, what you saw tonight, I mean, everything was all the pre-processing was done. I took a lot of shortcuts so you didn't have to see, you know, the process that might take 5 or 10 minutes just to do. But you're never really at an endpoint. You're just kind of like, well, I'll just put that aside and I'll come back to it. Some images I can collect data for maybe 10 hours and take only 5 hours of processing. And there's some images when I've collected like 76 hours worth of data, night after night after night, in order to get enough information to really do a fine image. This is a time-consuming, and it's a process of patience. You don't whip it, you don't take out your camera, take a picture, and then look at the result.
And then we had one other question. In that last video you showed, was that the Pleiades, very close to the end of that
No,
video?
that's not the Pleiades.
Okay.
I tried to include mostly just emission nebula. The Pleiades is a reflection nebula. That is, it just reflects the starlight from neighboring stars, and they're usually blue. I have plenty of reflection nebulas, and they make very nice targets, but they generally don't have many emissions. And if you want to do a reflection nebula, you're doing them in regular RGB. Sometimes you'll include hydrogen alpha if there's a little emission. No, that wasn't the Pleiades.
Okay, I think that's
Should I stop sharing?
all the questions we have. We can probably flip over to Drew. Give me a second.
Thanks very much to Eric for the good program he just gave us. And hopefully we're going to have it available for people to review online. I wanted to remind people, our viewers, if you're still paying attention, that we still welcome feedback from you via email. And that's easy enough to remember, the feedback@naperastro.org address. Or you can list things in the Facebook comments, but they might tend to get more lost there. If you want to just send us messages. And a reminder of the upcoming events that I covered at the beginning. Our usual monthly programs, again, seems very likely we're going to be doing things online for quite a while. We do hope to get some more pop-up observing events in. Again, we're not planning those and putting them on the calendar ahead of time because we have to wait to see when it's going to be clear. At the moment, it looks like it might be clear this Friday night. So if you're fond of our ventures out into the wild, we might be doing a stream from the observatory. This time would be geared more towards doing some actual observing with our video setup. So it would probably be a little later into the evening, maybe like from 9:30 to 10:30 or something like that. Keep on watching us on Facebook, and members, keep your eye on the club message board. Otherwise, I wanted to thank everybody for attending and hope to see you out under the stars before terribly long. But for now, good night. We're signing off.